Alright, hi everyone. So we are coming for today's day 3 of ZK learning. So today we're going to be talking about the Building Snark Part 2 by Dan Bonnet. This is from the ZK Whiteboard Sessions, the first season, Module 3. So I'm going to be sharing what I learned. So if you're gonna be revising what Snark is, we have the functional commitment scheme, and we're gonna have the polynomial interactive protocol proofs. So what is going to be the PCS is going to be prover is going to be sending polynomial as a commitment to the verifier, and then that's the cryptographic part. And the polynomial interactive protocol proof is that's how the verifier verifies it. Technically, way to prove that prover knows secret witness, and that fulfills the circuit, and they have to go through back and forth with the verifier choosing random point, and prover is trying to prove, okay, I know this is the correct polynomial. This is the root from there. Let's talk about one observation, things I learned. This is called random point testing. Let's say we have a polynomial degree of d. It can be 3, let's say it's 2, then it's going to be let's parabolic the quadratic formula. And it can have most d roots, so it can have mostly 2 roots. And if the field size is big, let's say if it's going to be 2 to the power of 256, it's going to have freaking massive. And then if you're going to randomly choose a point from a field, let's say it's freaking massive and it's becoming a root, is very, very, very low chance. It's close to 0. It's almost 0. Because if you have 2 roots, if you can have 2 out of 10 to the power of 80, so it's going to have 1 and then 85 zeros out of 2, it's almost 0. So what it means is, if we have a polynomial and if we randomly choose a point from the field and give this input to the as a commitment to the polynomial and says, hey, check this root out, and if this root, we have the roots, if this root is actually giving a 0 from the polynomial, the result is being 0, and then we can assume that we can be sure that, okay, this polynomial is actually true because we are randomly choosing out of the roots, and if this polynomial is true, it's going to give us 0. If it's not actually using the roots, then it will not return 0. So we can think this is a prover can prove. Prover is not lying. Okay, so in the most cases, polynomial IPs called Plonk is being used in this polynomial IPs. And step 1 in that building Plonk is compiling the circuit to generate a computational trace. So we will have the circuit, and then we're going to have a trace table. So you're just going to use a trace table to easier to do for the calculations. And then we're going to encode those inputs of trace tables as a polynomial. We have the trace table, let's say input to the gate, input to the gate B, input to the gate C, and more and more. So all the values, we're going to create a polynomial from each value. We can encode the input and count the wires or gates. So we're going to have, I don't know, 5, 6, even more, like around 12, depending on the number of gates, the polynomials. And then the main step here is we have to prove the validity of the prover's polynomials. So we have, I don't know, around 12 polynomials for each gate in the input. We have to prove that encoding, like the prover is encoding the correct inputs, because inputs are correct, and every gate is evaluated correctly if the calculations are done correctly, and then the wiring is completely correct. So because one gate's result is going to be the next gate's input, so it's correctly connected, and then the output of the last gate, it's going to be 0, which means the whole polynomial has to be 0 polynomial. Like at the end, it has to return 0. Well, that's the half of the video. That's the most things I learned. I understood actually, but I didn't get most of it. So tomorrow we're gonna try to finish how to prove all of these points, and we're gonna be moving forward. That's all. Thank you everyone, and see you tomorrow.